All right. Lecture 14, atomic masses. So you should know these definitions. I only have one problem here because they're all the same. I mean, if you know what you're looking for, then no matter what you're given, it's set up the same way. What we're trying to find is the atomic mass, or the average mass, of magnesium from the isotopic masses here, the masses of each of the individual isotopes. There's magnesium 24, 25, 26. And then the fractional abundances, we'll just write Fa here. So this is 78.989%, 10.001%, and 11.010%. So the way that you find what you have to do is you have to multiply these and these, this times this, this times this, this times this, and then add them up. But what happens, a lot of the time people will add these two together, these two together, these two together, multiply, they'll divide. It's all kinds of crazy stuff that happens. All you have to do is multiply them each, the mass times its fractional abundance, and it'll be set up just like this, or in a table like this, and then add them up. The reason we have so many significant figures is that we don't want to lose any when we add them together. If we only had 3 here and 3 here, we could end up really losing a lot of information. So we want as many as we can have here. So it's going to be 23.98504 AMU times its fractional abundance, 0.78989. And then 24.98584 AMU. And I'm doing it quickly. I'll double check to make sure if I'm putting the wrong numbers in here, but let me just get them down here first. 0.11010, so 29. Looks right. Right. Got to be careful because there's so many digits here. And you might say, well, why don't we they're looking for the atomic mass, that's given in the periodic table. Well, on the exam, what I generally do is I say that this sample came from outer space. It was found in a meteorite, which means it doesn't have to have the same fractional abundances as they have on Earth. It's found that that's actually rarely the case. If something comes in you have elements from a meteorite sample, they tend to have different fractional abundances. So your answer can't be written directly off the periodic table. I wouldn't suggest trying it. You want to I want to see the work and make sure that you're doing it correctly. So I'm going to do this out for, now there's 5 significant figures, so there's be 18.946. You can see where we've already lost, or apparently lost, significant figures. We have just as many as we're supposed to have, but I guess decimal places is where we lose out. And this is 2.49. We have 5 and 5. Well, we have 5, so we have to do 2.4988. We're multiplying, so we don't go by decimal places. And you get 2.8607 AMU. And just to make sure, I'm going to go through this real quick, make sure that I got the right numbers. 894, yep. In this case, I hate to, you can always fast forward, but I just want to make sure that I get the right numbers, because it can be very confusing, even though the setup is correct, to have the professor get it wrong. Once we have these, then we add them. You don't multiply them, you don't divide them, you add them. So 18.946 plus 2.4988 plus 2.8607, and this comes up to be 24.3, and we have 3 decimal places here, so we have to stop 06 AMU. Now for from the periodic table, your periodic table, well, in the book it's 24.305, and this is 24.306. Very close, but on the exam I'm free to give any fractional abundances, any masses, because I'm going to say it's from an an extraterrestrial source, so don't count on being able to even check it against the periodic table. Sorry, right there. So it's very simple. If you're given 25 atomic masses, multiply them by their fractional abundances all the way down and add them. That's all there is to it.